Hello, good afternoon. Any one of you, please, is my whiteboard visible with today's date?
Yes, sir.
Okay, so I will start in 2-3 minutes. People are joining. Okay, so let me start. So last time we discussed about a simple wire, and which is typically a simple wire we do represent like a simple wire at low frequencies. But at high frequencies, we have seen that it is represented by some parasitic resistance and some self-inductance of its own. And then we also discussed that here we speak a diameter in terms of mil, which is very important because our dimensions are very small at high frequencies. Lambda is very small. So even millimeter and centimeters are big value for us. So we speak in terms of mils. And as you have discussed, 1 mil is nothing. It is 1/1000 of an inch, or it is 2.54 centimeter by 1000, or I could write in terms of the millimeter also, 0.254 millimeter. Now let's start with the new component, which is a very basic component, resistor. And uh, typically, as we have seen, a resistor is represented by a symbol like this, an equivalent circuit at DC or low frequency. But what will happen to my equivalent circuit of resistor at high frequencies, like we are talking about megahertz, gigahertz, or sometimes we also say AC frequencies. So it could be represented like this. Now, if you see here, typically a resistor is like this. It is a metallic enclosure or something, a plastic body, which is like a color coded, and which could be a black, brown, red, orange, yellow, green, blue, and so on. And another line, which is a silver or gold line, which decides my tolerance, plus minus 5% or plus minus 10%. So this is a typical. Normally we use a multimeter to read the value, measure the value of the resistor, or uh, sometimes we simply read these values and find out. The first two color code decide my significant digits. Like if it is black and brown black, so it becomes 1 and 0, because there are color codes are there. I don't want to go into the details, you'll find out. So there are color codes, and each color has got some numeric number. Like black has got 1, brown has got 0, and so on, like that. So here my resistor is like this. It has got two leads and so on the either side. That means there is a wire here and there is a wire here. So how to represent the equivalent circuit of resistor at high frequencies? So if you see here, it will be represented like this. So this is my nominal value of resistor. I am denoting by capital R. And then we have, because there is a wire on this side, so there is a inductor and there is a resistor, as you have seen for a wire. And there is a inductor and a resistor on this side also, because these two represents the wire on the two sides. So one is this wire, another is this wire. So these are represented by these two wires, assuming typically both the wires are of same length and same diameter. So I'm putting the values R and L same on the either side. Now, if you see here, when we are going to use a circuit, resistor in a circuit, basically I'm going to solder like this. So this is metal and this is metal, and between the two metals you have air or dielectric material. So basically it will act like a capacitor. It will act like a capacitor here. So my equivalent circuit will become like this. So I will have a capacitor. So this R is my nominal value of the resistor, and here this L and R and LR are representing my wire on either sides, and this becomes my capacitor, because when we solder it, it is not short circuiting. It is basically touching the two metals, and between them there is no metal. So it is like a this thing. Now here, all those things for resistor, ideally it should be like this, because this is my nominal value of the resistor. So these elements becomes my parasitic or stray elements, as we have discussed last time. Like for my wire, L and R are the stray elements. So in this case, this becomes my stray elements or parasitic elements. At high frequency, or this is at low frequency. So that means my resistor is not a no more simple resistor. It has also got some inductor and some capacitor and some. So my resistor value is also changed from R to R plus 2 small r. So that also changes. Not only that, it is accompanied by an inductance and capacitance, and which we know are dependent on the frequency, because uh, it is, we call it inductive reactance and capacitive reactance, XL and XC, which we are going to discuss in the next slide. So this becomes my equivalent circuit. So it is not that easy. So you have to analyze at your frequency of interest what is the value of the resistor should be there. So moving further in the next slide. Okay. So here, because in my resistor, we are having all the three things. So we speak in terms of impedance. Rather than speaking in terms of simple R and anything, we normally speak in terms of the impedance, which is typically denoted as capital Z, and in units are ohms. And there we have R, XL, and XC. This XL is what we call the inductive reactance. So this becomes my, and this becomes my capacitive reactance. And this is nothing. XL is equal to, we call it J omega L, and XC is equal to 1 by J omega C, or minus J omega C. Okay. J is nothing. It is the imaginary number. So this is the imaginary quantity. And here my omega is 2 pi F. So basically, how I use the resistor at what frequency, that becomes now very important. Like at lower frequencies, in basic electronics, you suppose you need 10 kilo ohm, you just put 10 kilo ohm, and then whether you are working at 10 kilohertz or 1 kilohertz or 2 kilohertz, or it always works fine. Okay. So here, this is like what we call the impedance. That means impedance is always represented as R plus JX. If it is positive, that means it is inductive reactance, or R minus JX. That means it is a capacitive reactance, capacitive. And here it is inductive, the plus sign. So the plus sign denotes the inductive one, and negative sign denotes the capacitive one. So we normally speak in terms of impedance. That means for us, the resistor is no more a simple resistor. It has taken the form of impedance. And I can't measure the resistor at using the multimeter, because multimeter measures at DC or low frequency. But if you are going to use at the kilohertz frequencies, like what you have used in the basic electronics, you will find that it is the same. But typically when we talk about the today's frequency applications, like wireless LAN, your GPS, your Bluetooth, your Wi-Fi, your millimeter wave frequencies, 5G, 4G, 3G, whatever you speak, these are all RF frequencies. And there the frequencies are of the order of gigahertz, 10 to the power 9 hertz. Okay. 5 gigahertz, 2 point, like your processor is having 3 gigahertz processor, and so on. So you have to work out what is the value. You have to find the equivalent circuit for that. Let's understand through one example. As I said, I always appreciate one example. So let's take, I simply pick a resistor. I have a metal film resistor, let's say a simple common resistor, and it has got two leads. Okay. Now let's say this resistor is of 10 kilo ohm. Okay. So this is 10 kilo ohm that is given to me. And I want to use this resistor, let's say at 200 megahertz, not very high frequency, but let's see, even at megahertz, what happens. So it becomes 200 into 10 to the power 6 hertz. Now, if I use this resistor at just like that, without using, understanding the equivalent circuit of resistor, which we have just discussed, then it will be a disastrous, which will understand how. So this becomes my 10,000 ohm. Okay. So what we will do here, we will first measure the length here, and I measure this length, let's say it is 0.5 inch. I measure the length of this lead also, because both the leads are same, and let's say it is given to be 0.5 inch. Okay. And typically, as I said, there is a parasitic capacitance, which is I'm denoting like this. Okay, so this is the parasitic capacitance, which is C. And let's say it is supplied by the manufacturer. It is 0.3 picofarad. These are typical values, as I said. 0.3 picofarad means it is 0.3 into 10 is to power minus 12 farad. So this you must be knowing, it is in farad. Okay, so this becomes my capacitor in farad. Okay, so this is normally provided by the manufacturer. Okay, because when you fold the leads, it will come out with only a particular distance. So C is equal to epsilon A by D. Am I right? That is area which depends upon the diameter or the radius of the wire, and the D is the distance between the two metals. So this is like provided by the manufacturer. I measured the diameter of this wire and I found it is using the screw gauge, as we have understood. I found it is SWG14 or AWG14, which I found it is 64 mils, if you recall, and which means it turns out to be 64 into 0.254 centimeter. Okay, so that turns out to be my 0.1628 centimeter. So I convert this diameter into the centimeter again, because as I told you, this is what we given as here is 0.254 centimeter, okay, or 0.0254 millimeter. So that is 1 mil. So how much trouble I have to do now? For a simple resistor which I want to use at 200 gigahertz, 200 megahertz, I have to first compute what is the length of the wire, and then I have to measure the diameter of the wire, then compute the inductance and so on, that we'll discuss how, and the capacitance value which is provided by the manufacturer. So this is, I'm showing by the dotted line. So this is my wire, and this is a stray capacitance. Okay. Now let's see how to work out this thing. Okay. Now typically, what we do here, if I want to solve this problem, we use a standard formula for inductance. Again, no need to remember this. Something are not to be recalled and all those things, but it is available in most of the books as an appendix. It is given as 4L by D minus 0.75, and this is in microhenry. That means my L is given in microhenry, where L is equal to the length of the wire in centimeter, which we have just converted into the centimeter, and D is the diameter of the wire, which is in centimeter. So if I put this thing in the previous slide, which we have completed, so 0.5 inch turns out to be 1 inch is 2.54 centimeters, so it turns out to be 1.27 centimeter, and this is also 1.27 centimeter, and this is the diameter which we calculated as 0.1628 centimeter. So again, as I said, this is a standard formula. No road, please. You don't need to remember this thing. Whenever it is there, it is provided by the manufacturer or and so on. And it is standard formula. So in my case now, your L for this resistor becomes 0.02. Sorry, this is 0.02 into 1.27. Only thing we have to understand how the things become so serious for us in high frequencies, and that becomes 4 into 1.27. So I just substituted all the values, 0.1628 and minus 0.75, and it will give me the answer in microhenry, okay, which is 10 to the power minus 6 Henry. So I got this value 0.087 microhenry. I convert into 8.7 into 10 to the power minus 9 nanohenry, okay, because micro is nothing, it is 0.087 into 10 to the power minus 6 Henry. So it becomes like this. So Henry only. So that means it becomes 8.7 nanohenry, the significant value which we calculated. And C, which is provided by the manufacturer, is, let's say it is given as 0.3 picofarad, which is 0.3 into 10 to the power minus 12 farad. Okay, so I think just for everybody, even if he misses, it is for the Faraday, and this is nothing, it is for the Henry in inductance and so on. So I got this C value, I got this L value, and so on. Now we have to find the use the equivalent circuit. Okay, let's understand how to use that. But before we use the index, so this L will present an equivalent reactance. Okay, L presents an equivalent reactance, and this equivalent reactance is nothing, it is the inductive reactance, because L always present the inductive reactance. Okay, at 200 megahertz, because our frequency is 200 megahertz, that means F is given to be 200 megahertz, is given by XL is equal to J omega L. So I have to calculate this thing, because normally we don't put the value of inductance, but we have to put the value of inductive reactance. So in my equivalent circuit, everything will be ohm. L will be represented by XL, which is in ohms. R is already in ohms. Capacitor will be represented by capacitive reactance. And capacitive reactance, as I told you, is typically negative, which is again in ohms. So this is given by, so I just put these values, so it becomes 2 pi into 200 into 10 to the power 6, which is my frequency value, and into 8.7 into 10 to the power minus 9. So this is my L, this is my frequency. Everything I converted into Henrys and Hertz. So your XL, if you calculate, I got the answer with me, J 10.93 ohms. So that means it represents an inductive reactance. So this will be by J 10.93 ohms on the either side of the resistor. Similarly, we calculate capacitor, which is my C. So this is your inductor, as you have seen. It will present again an equivalent reactance, but this reactance will be a capacitive reactance, which we say it is typically negative. Okay, at the same frequency, because my frequency is different. So suppose you have to use this resistor at some other frequency, let's say 400 megahertz, you have to rework all those things. Somebody has to use that 100 megahertz, he has to rework all these values again. So it becomes XC is equal to J minus J by omega C, or it becomes 1 by 2 pi FC. So it becomes, you put all those values, 1 by 2 pi into 200 into 10 to the power 6, and again my C value, which is 0.3 into 10 to the power minus 12. So I will get the value of minus J2563 ohm. Please note that it is a capacitive reactance, so it is always a negative value. Okay, so I got this XL and I got this XC. First we calculated IL by measuring the length and the diameter, putting in that formula, which I said again, no need to remember, and wrote these values. These are standard formulas which are available in various books. And then we work out the inductive reactance and capacitive reactance. So once we have got this, now I can look into my equivalent circuit, and my equivalent circuit will look like something like this. Therefore, my equivalent circuit of resistor, which was 10 kilo ohm, okay, at 200 megahertz, because now it is given by something like this. This I calculated. This is given 10 kilo ohms, which is given. This I calculated J 10.93 ohm, corresponding to the inductance, and again corresponding to the inductance, I got this one, and then corresponding to the capacitance, I found this is minus J2563 ohms. Okay, so that becomes my equivalent circuit of the resistor at 200 megahertz. Now we have to solve it. So Abhi, I don't have the time. So what we do here, your J 10.93 ohms is much less than 10 kilo ohms. Okay, 10,000 ohms. So I'm neglecting this. So we can neglect on this side. That means 10 ohm is very small as compared to 10,000 ohms. So just neglect it. And once we neglect it, the equivalent circuit of this becomes nearly equal to, so that we can easily solve like this. And this is my 2563 ohm, which is representing my capacitance. So no need to write minus sign here. And this becomes my 10 kilo ohm, which is my value of R. So basically I have 2563 ohms in parallel with 10 kilo ohms. Okay. So this is nothing. It is basically equal to in parallel with a 10 kilo ohm resistor. Now I can solve this thing because it is two resistances in parallel. And if I solve this, your Z, because now we have to speak in terms of Z, so it becomes RXC over under root of R square plus XC square. So this becomes 10,000 into 2563 over under root of 10,000 square plus 2563 square. Okay. So I'll find this thing is something, if I calculate, it turns out to be 8090 ohms. That means such a serious problem, your 10 kilo ohm resistor, which I have checked with the color code, which I have checked with the multimeter, it was showing to me 10 kilo ohms. Okay. But I found actually it behaves like a nearly 2 kilo ohm resistor at 200 megahertz. So that is a very serious problem. Because if I'm measuring with a multimeter, I am using the DC. That means the zero frequency, I'm measuring that value. But finally, I have to use this resistor at 200 megahertz. That means 200 into 10 to the power 6. So can you assume how this value will change when I'm working in gigahertz? Because today we are working in gigahertz. Our whole communication system is RF frequencies, gigahertz only. Okay. And that is a very, very serious problem. Just to give you one example, if I plot, so basically I am not speaking now in terms of resistor, I have to speak in terms of impedance value of resistor, okay, which is in ohms, which in this case, because your capacitive reactance is dominating, okay, and I neglected the inductive part because I found inductive is not that much dominating. So if I plot this value of resistor frequency, just to give you one example, and if I plot the impedance value of resistor, which is nothing, it is equal to Z, it is in ohms as we have just calculated. So basically what happens if I plot this thing, let's say from 1 hertz to 500 hertz to let's say 100 megahertz. Let's say I'm plotting like this. Let's say 1 gigahertz and this is 200 megahertz. So what is happening here? Ideally, so this is my 10 kilo ohm. Let's say this is my 10 kilo ohm. Okay. So ideally, my value should be like this. So it should be 10 kilo ohm across all the frequencies. That is what we call the ideal. But what is we have seen, it is now not happening in this way. Typically what happens, as we have seen at lower frequencies, it tends to remain like this. Then it will start decreasing. And it will come to a point and then it will start again increasing, something like this. So this is the behavior. Though I calculated for 200 megahertz, and if you found at 200 megahertz, I found this value of resistor, instead of 10 kilo ohm, it is found to be 2 kilo ohms. Okay, that is something what we just calculated. And it will happen like that. So your impedance will decrease with the frequency. Okay. So what is happening? My impedance will decrease with the frequency. And when the impedance decreases with the frequency, okay, it is more capacitive because XC is equal to 1 by omega C. So capacitive effect is more dominant in this case. So when the impedance is decreasing. So here my impedance is decreasing. So I would say in this range, your impedance decreases with the frequency, and it is nothing, it is a capacitive effect. Okay, that we know. If my impedance decreases with the frequency, that means Z is equal to XC, which you have seen is equal to 1 by 2 pi FC and so on. So it is decreasing with the frequency. 1 minute, let me put it like this. So it is a more capacitive effect, as we have seen now. In the previous example, we found that the capacitive is more dominant. Okay. And slowly what happens, as you further increase the frequency, it may happen that the inductive effect will become more dominating and capacitive effect will become less dominating. So a point will come when my inductive reactance becomes equal to the capacitive reactance. So just to mention that, I move to the next slide and then I will explain to you. So a point will come when my inductive reactance becomes equal to XC. That means J omega L is equal to 1 by J omega C. Okay. Okay, as we have seen earlier, your capacity reactance is denoted by 1 by J omega C, as we have seen here. We calculated this thing, or minus J omega C. Okay. Because J square is equal to minus 1. So please note that this is something we know, the imaginary value, iota square or J square, whatever you prefer to put, it is the same thing. Okay, so at certain point, what will happen? Your inductive reactance becomes equal to the capacitive reactance. That means ZL, XL becomes equal to XC, J omega L becomes XC, or I will find that omega square is equal to 1 by LC, or omega is equal to 1 by under root of LC. And that you must be knowing. I could say your F equal to 1 by 2 pi under root of LC. So that is my resonance frequency. So resonance will occur when your inductive reactance becomes equal to the capacitive reactance. So as we see in the previous slide, if I go to the previous slide, a point will come where my inductive capacitance becomes equal to the capacitive reactance. Here, if you see in the down slope, we have found that the capacitive more dominating, inductive less dominating, and that's why we neglected in the inductive reactance in the previous example. But after a certain frequency, inductive effect will more becoming dominating, because this is the inductive. Inductive means positive sign. That means Z is equal to XL and it is J omega. So it increases with the frequency. So if my impedance is increasing with the frequency, it is inductive. If it is decreasing with the frequency, it's capacitive. If both are same, then it becomes to the resonance. So at resonance, we'll get it. So can you imagine, today we are in this region. Today we are in this region. Nearly we are working in this region. That is 1 gigahertz and beyond, or something like few megahertz to 1 gigahertz. Now, that is a serious problem. My 10 kilo ohm is almost may behave like a 0 ohm. That is a short circuit, Or it could be some other value of 100 ohms or 200 ohms or minus 100 ohms or minus 200 ohms, inductive reactance or capacitive reactance, depending upon either this side of the resonant frequency or that side. And that is a serious problem. That even a simple wire, a simple resistor is giving me a serious problem. Now, because of this seriousness and other things which you have discussed, the skin effect and other thing, your RF designs are more complex and your RF systems are more costly and so on. So this is something. Again, this we have taken one example, but just to make you understand slightly better, let's plot this frequency versus the impedance of resistor. So as you see here, like this is a, let's say, a 10 kilo ohm resistor. Okay, so this should be the ideal behavior, but we have found this is not the ideal behavior. It is actually working like this. It is actually working like this. So this is more practical behavior. So suppose I use a larger value, say 20 kilo ohms or something, your behavior will be slightly different. So suppose I take 20 kilo ohm, its behavior will be something different. That means it will start deviating much earlier, let's say higher value. Just to give an example. And if I further increase to a further higher value, let's say, so it will further decrease. So it will be much more serious problem. So as we increase the value of R, and these are the typical examples of my what we call a simple resistor, metal film resistor, metal film resistor of 100 kilo ohm, of 10 kilo ohm, let's say. Okay. And here, but metal film resistors are suitable only when the power is very small, a quarter watt or this thing. But if we have a circuit in which higher power is used, then we use a carbon composite resistor. Now, suppose I use a carbon composite resistor of 10 kilo ohm because the carbon is there, then my situation will be very worse. So this is the behavior of a carbon composite resistor. That means inside the carbon is there. So it is a higher power handling capability, about half watt or so, as compared to a quarter watt power handling capability of a metal film resistor. So this is for the carbon composite resistor of same value, 10 kilo ohm. But 10 kilo ohm of a metal film resistor is slower decay, but it is faster decay. So from here it is very clear. My resistor is no more a simple resistor. It has also inductive and capacitive effect. Only except at one particular frequency when there is no inductor and capacitor. So I can fairly very well say your V is not equal to IR. Ohm's law is not valid. And simply your KVL and KCL are not valid. But still we have to understand this, and we have to, when we design the RF system as we see here, or high frequency systems, though I'm saying your Ohm's law, KVL, KCL are not valid because R is no more a pure R, it is an impedance. It has inductive or capacitive dominance, okay? But still we have to use this to see to it how to use the circuits at RF frequencies. So that was about the resistor, and that is a big problem. Now coming to the next component. What is my next component? Let's say start with a capacitor. So I will not take the example here, but just understand this capacitor. Now, what is this capacitor? Capacitor is nothing. We all understand. It is a two metal plates which are typically separated by a dielectric. So there is what we call a dielectric, which you must be knowing. Typically, we use lower metallic plate as the ground plate and another one, and then we apply a voltage across this capacitor and so on. Now, this dielectric is nothing. It is characterized by what we call the dielectric constant. Okay, dielectric constant is a more generic term, but more technical term we say electric permittivity. Okay, which but we use or relative electric permittivity. So it is typically denoted as epsilon r, and that is how we define the dielectric constant. Okay. Now, epsilon r, as I said, it is equal to 1.000 if your dielectric happens to be a vacuum, or it could be 1.01 if the dielectric is air, or let's say it is 80 for water and for different material. So what is dielectric? So dielectric, as we know, that capacitor is nothing. It is two metal plates separated by a dielectric. So what is the dielectric constant? So dielectric constant is nothing we can define because the charge is stored in the medium. When we apply a voltage across the capacitor, the charge is stored in the alternate cycle. Okay, that is how we define a capacitance and so on. So if I have to ask you what is the dielectric constant? So dielectric constant is nothing. It is the charge retention capacity of the medium. Charge retention capacity of the medium. So if you noticed here, air doesn't, air the dielectric constant is typically 1. So the charge retention capacity is 0 almost. And for water it is 80, and that means the charge retention capacity of the water is very high. And that's why we sometimes get the shock when we put our hands in water and the voltage is applied. because capacitance is always defined when a voltage is applied with respect to the ground to one of the metal plates. So this is something you are aware of, the dielectric constant, this one. Now, we all know that the DC equivalent circuit of a capacitor is simply nothing. It is defined as like this. Or if it is a polar one, we sometimes say, if it is a polarity, then we have got a plus minus. So this is my DC equivalent circuit of the capacitor. Now here, what is my AC or RF equivalent circuit of capacitor? So how we can define? So this is my nominal value of capacitor, which was like this earlier. Okay. Now this capacitor has also two leads, because normally capacitor is also in the two leads, which you normally solder it. So I will have one lead on this side, which is characterized by L and R, another lead on this side. So there is two leads are there. So again, this one. So this becomes my L, this becomes my R, this becomes my L, this becomes my R because of the two leads. So this represents my the two leads on the other side. Now, because in the capacitor there is a dielectric. Because in the capacitor there is a dielectric, and dielectric is not a perfect conductor and perfect, or it is neither a perfect conductor nor a perfect insulator. So it also has a certain insulation resistance of its own, because it is not a perfect insulator. So it has a certain insulation resistance of its own. So we put the additional thing here because it is part of the capacitor as in my equivalent circuit as here, which is what we call the RP. So RP is nothing. It is my insulation resistance of capacitor. And again, the two leads, when we solder it, it will also give you some other capacitance also, a small c and so on. But let's concentrate on this one. So in this case, my simple C is not simple C. It has got many parasitics. So this becomes my parasitic elements for the capacitor. Whatever extra element I got it. Additional R on the either side because of the lead material. Additional L on both the sides because of the lead self-inductance, the wire self-inductance, and RP. RP is the insulation resistance of the dielectric, because it is not a perfect dielectric. So it is a dielectric, so it is not a perfect conductor, not a perfect insulator. And if it's not a perfect insulator, that means it has some insulation resistance of its own, which we denote by RP. And when I solder it again, you will find additional capacitance. Let's say it is a nominal value, like in the previous case, it is 0.3 puff. But I mean to say, your capacitor is also no more a simple capacitor. It is also, we have to speak in terms of the impedance again. That is what we call the capacitive reactance. So if I do the same example, like we took the example of 10 kilo ohm and 200 megahertz, I'm not going to do that thing, but just for your understanding, what will happen? So if I plot the frequency versus, again, now we have to speak in terms of impedance. So our language is becoming different now. There we used to talk about simple RCL, and here we are speaking in terms of impedance. That means my values of RCL also has inductive reactance or capacitive reactance. That means they are dependent on the frequency of this thing. So if I plot the impedance of capacitor, just like we have plotted the impedance of resistor with the frequency, what will happen? I will get a plot something like this. So ideally, the capacitor value should be like this. Capacitor always impedance decreases with the time. So this is my ideal or perfect capacitor. I will explain to you what do you mean by ideal here. But nothing is ideal in this world. So ideally, the capacitor should behave like this. That means your impedance decreases with the frequency. Again, the same thing, Z equal to 1 by j omega c. Okay. But practically what will happen here, as we have seen for a practical resistor of 10 kilo ohm, if I plot the practical one, let's use a different color. So let's say this is my practical capacitor. And this practical capacitor will remain like this at lower frequency. So this is the basic electronics part, the lower electronics. There you need not worry. Here it remains the same as we've seen for the resistor also. Then it start decaying much earlier. a resonance will come again, because here also inductance is there, capacitance is there, inductive reactance is there, inductive capacitance will be there. The moment I have inductance and capacitor in my circuit, I am bound to get the resonance, which is decided by when my inductive reactance becomes equal to the capacitive reactance. So here also I will get this thing. And previously, if you've seen this for the resistor, uh, this resonance will become nearly equal to the zero here, zero value. But here, this value is not zero. It remains certain value, but yes, it decreases. So what we see here, if I use a different code, so if I cut this into two half, here my behavior of my capacitor is capacitive because impedance is decreasing with the frequency. But here, as we have seen earlier, my capacitor will behave like an inductor. So this is the practical capacitor. This I would mention here as a practical capacitor. So practical capacitor will behave like a capacitor only, but of different value, because now values have changed from the ideal value, but it still behave like a capacitor, but it will be totally different value, like 10 kilo ohm becomes 2 kilo ohm there. But after a certain frequency, this capacitor will behave like a what we call the resonance frequency. When your R is equal to XC, this capacitor will start behaving like an inductor. And it will not reach to this value. It will be a value which is an impedance here. This is what we call the equivalent resistor of the capacitor, which is nothing as Rs plus Rp. I will explain in the next slide. I will explain this equivalent series. So it will not go to zero. But basically, today we are in which region? Today we are working in this region. So that is my frequencies of interest today. And that is very strange. Either your capacitor is now behaving like an inductor. So if you blindly put the capacitor in the circuit without using all those calculations, just like we have done for the resistor, you will find, but actually it is behaving like an inductor. पूरा actually change ही हो गया, मतलब पूरा word change हो गया. Okay, your capacitor is which we used to think, it is not behaving like a capacitor also. At least up to a certain frequency before the resonance, which could be few megas, it will behave like a capacitor. But after that, in today's frequency of interest, we are working in terms of it may behave like an inductor. Totally different behavior. And just now we defined what we call the ideal capacitor. So ideal capacitor or perfect capacitor, how we define? I think you must have learned in the basic electronics, this relation I is equal to J omega CV. And for a ideal or perfect capacitor, we could write this as omega CVE J 90 degree for perfect capacitor. What it means for a perfect capacitor, your the current I leads the voltage by exactly 90 degree. That's how we define, which you must have learned in this thing. If it is deviating from 90 degree, then it is not a perfect capacitor. So because you are applying the voltage across the capacitor, so there is a voltage, there is a current. So if the current leads the voltage exactly by 90 degree, that means like this, you are having a perfect capacitor. But if it is different, and so on. So how to decide my capacitor? Now when I have to go to the market, I have to find out which is the best capacitor for my this thing. So for your capacitor is characterized by various parameters. Okay. And all these parameters are related to one another. Let me explain. Characterized by various parameters. Because when you have to go to the market, I have to say, I want this capacitor. So obviously you can't say that I want to use the capacitor at 200 megas, but sometime when you come back, you decide to move to 300 frequencies and so on. So you have to look certain parameters. What parameters? So one of these parameters is what we call the power factor. So I'll move to the next slide because here I may not be able to write down. So So what are those parameters? So that we'll discuss in the next slide, one by one. So ideal capacitor we have understood, and we have actually found out something, that it is at resonance, it is not going to zero. Your impedance is becoming something like RS and RS plus RB. Obviously, XL and XC will cancel. Only R will remain, but R consists of two parts, RS and RB, which we'll understand slightly later. Okay, so let's understand various parameters by which the characterized capacitor. One is what we call the power factor, and that is very common in electrical engineering also, PF, and we denote as cos phi. So basically, what is this? So this is my I plot R versus X here. Okay, typically X is negative for the capacitor, as I said, JX. So this is how we define an impedance of a capacitor, Z, an impedance. So this is what we call R equivalent, which I will just explain. This is a factor phi cos, and here it depends upon the XC square plus R equivalent square. Okay, why it is not writing? R equivalent square. And this is my XC. Okay, so this is how we define, and this R equivalent is nothing. It is equal to RS plus RP. RP we have understood, it is the insulation resistance of the dielectric. Okay, insulation resistance of the dielectric. And R is the series lead resistance. That means the small r which I have taken, which is denoted as R plus R. Okay, so series resistance of the two resistances there. So I club them also. So those resistance will be there. So it will never go to zero. It will be, there is certain resistance will always be there. Okay, but XL and XC will vanish. So I define my power factor, which is as per this graph, cos phi is equal to R equivalent over under root of R equivalent square plus XC square. Okay. This usually R equivalent is much less than XC, because these are parasitics. Parasitic values are very small, so sometimes we can ignore it. Like in the case of, in that example, we have ignored the inductive reactance and so on. So in this case, I could write down my power factor nearly equal to R equivalent over XC also, because of this relation, R equivalent is equal to under root of R equivalent square plus XC square. So if my R equivalent is very small as compared to XC, I can say that my power factor could be written like simply like this. Okay, so this R equivalent, what we have learned just now, is also called ESR. Some books write like this. So this is nothing. It is called the equivalent series resistance, but basically it includes both the resistances. So this is one parameter. So for an ideal capacitor, R is a parasitic. So ideally, power factor should be equal to 0. Okay, because R is a parasitic. So I can write down this for ideal capacitor. C is the desired value. R is a parasitic. R is parasitic. And so for ideal capacitor, R equivalent, or what we call ESR, must be equal to 0. That is the one condition for the perfect capacitor. So when I am buying a capacitor, I have to ensure that its power factor value is, by the manufacturer, is as small as possible. Obviously, you have to pay a high price for that. If you want to buy a better thing, you have to pay a price for that. Okay. Now coming to the next parameter, which is what we call, so we have understood ESR, we've understood power factor. Okay. Now the next parameter, sometimes people talk about another parameter. So this is the two parameters that we've discussed. One is power factor, and second is R equivalent or equivalent series resistance. And sometimes we speak, some manufacturers speak in the what we call value of dissipation factor. As we all have different names. My friends may be calling by a different name. My mother may be calling by a different name. My actual name may be different. So here also capacitors, various manufacturers talk about various parameters, but as we see here, they are related to one another. So this is, as we'll see later on, but this is another parameter which we call the dissipation factor. Okay, R factor we've understood, ESR we've understood, and the dissipation factor. So dissipation factor is expressed in terms of percentage. So it is nothing, it is we defined as the ratio of AC resistance to DC resistance of capacitor. So if I have to put, it means dissipation factor is equal to ESR over X. DC reactance. So AC resistance, sorry, not DC resistance. Just 1 minute. Sorry. AC resistance to reactance of capacitor. And this is also called the, as I said, AC resistance also, because it is coming at the higher frequencies. So dissipation factor is nothing. It is defined as ratio of AC resistance, which is ESR or R equivalent, to the reactance of the capacitor, which is XC. And typically it is expressed in terms of percentage. So we express as this one. So ESR or R equivalent. So that becomes another parameter. Okay. Sometimes people also speak in more common way, which is what we call the quality factor of a capacitor. So it is defined as Q. And Q we define as XC over R equivalent. It is a factor, so it is not expressed in percentage. R equivalent or ESR. Somewhere I am using R equivalent, somewhere I am using ESR, but one and the same thing. So Q is equal to this one. So here also I could also write down this as R equivalent over XC into 100%. So it is one and the same thing. So if you see here, every equation could be obviously the quality, or it could be written as 1 by omega C R equivalent, okay, which is omega is nothing, it is 2 pi F and so on. So this is another parameter by which we have to go for that. Another parameter which is also very important and which we have to consider is called the loss tangent. It is slightly, I will explain to you, it's slightly more difficult in the sense it is denoted as tan delta. Please note that this delta is not the skin depth, is not the skin depth here, but it is some angle, okay? Not the skin depth, which we last time discussed, Greek small delta. So in this case, this is not the skin depth, okay? So what is this? This is nothing, it is tangent of phase angle. This is a rare parameter which we use, but we commonly use this thing in high frequencies when you design the RF systems and so on. So it is a tangent of phase angle, which I will just explain to you. Relatively between the capacitor voltage and capacitor current. So if you see, everything is related to one another, and typically it is given as tan delta is equal to sigma by omega epsilon, where sigma is equal to conductivity of the metal capacitor that is there in the part of the capacitor, and epsilon is nothing, it is the permittivity or of the medium, which we typically denote as epsilon R, epsilon naught. Epsilon R, as I told you, it is called the relative permittivity, or what we call the dielectric constant. Okay. This I think you must be knowing. And this is my absolute permittivity. Again, there is a value for that, 8.854 into 10 to the power minus 12 farad and so per meter and so on. But you need not remember this value. But basically, it depends upon the conductivity and the this one. Okay. So this is how we define this one. And also there is a relation between Q and delta. Q is equal to 1 by 10 delta. So it is more an empirical formula and so on. Now, if you see here, we have discussed various parameters: equivalent series resistance or R equivalent ESR, power factor, quality factor, dissipation factor, and so on. So when you go and buy in the market, you will find either of these values. So if I'm looking for a perfect capacitor or an ideal capacitor, I want that what should be my values. So for a perfect, so for a perfect capacitor, ideal capacitor, my R equivalent or ESR, because R is a parasitic for capacitor, it should be equal to 0, which means your power factor we defined as R equivalent over XC, it must be equal to 0. Since we define power factor is equal to R equivalent over XC, okay, and your Q must be equal to infinity, the quality factor, because we defined Q as something XC over R equivalent. Obviously, quality factor is infinite, that means the best quality and so on. So this is what we call the quality factor of the this one, and the dissipation factor also, because it should be as small as possible, so it should be nearly 0%. Because your dissipation factor is, we have defined, it is again defined as R equivalent over XC into 100%. So it should be this one. So try to buy a product which is something very, very interesting, and to note that it is there. Okay. So and we all know that we can't ignore the capacitors. Okay. So we all know what are the various applications of a capacitor. They are used typically as DC block, that if I want to block the DC, we have to use the capacitor. They are used in filters where LC is used. They are used in oscillators. Again, oscillating frequency is given as F equal to 1 by 2 pi under root of LC. So we can't ignore the capacitor. But last time I told you, today if you see the today's PCBs, you won't find the inductors and capacitor. Okay. But I said they are integral part. We use for DC block, we use for filter design, we use for oscillator design, everywhere we are using. And it is still we need these subsystems, filter, oscillator, DC blocks, and so on. So one thing to note that where these capacitors have gone. If you see earlier TVs, there were big capacitors, and if you see earlier desktop big capacitors, now they have vanished. They come in a different avatar. And that avatar, as I told you, is in the simple form of a line only. But capacitor can take value from 0 to infinity farad and so on. How that line will behave like a capacitor. So that is part of this course. So today's PCBs, if you see, you will find lines and lines and lines. So what these lines mean? And line means like everything has become a planar circuit. So basically, your systems have become slimmer because your L and C have taken a different avatar. They are formed in the form of a printed lines. I would be very happy if the same L and C circuits are there in my body. I could have changed my L and C to a different avatar, and I need not go to the gym for my weight loss, which is becoming very impossible. So, but that is something you have to rely on that. This is not applicable to the human body. It is applicable to the circuits and system. So now my circuits have become slimmer and slimmer and so on, because my capacitors and inductors, which used to take a lot of space, and now can be realized in terms of printed lines, which we'll discuss how later on. Okay. So moving further, so we talked about the capacitor, and then what is the next element? So next element is obviously is your inductor. So let's start with the inductor part, and I will want to finish this thing and then move to the transmission line, because transmission line has all these elements. Okay. So now we'll move to the inductor. Inductor, as I said, it is a represented like a coil at the DC or equivalent circuit for that, which we call that a simple wire in the form of a coil. So this is an inductor. And why do we use coil? I think that we all understand, to increase the magnetic flux linkage. And sometimes we use the ferrite core instead of the air core, so that we can further increase the magnetic flux linkage. And I think I'm not going to discuss all those things. You must have learned in the in the electricity and magnetism part. Now, basically, my inductor, if I look properly, it will look like this. It is a wire of certain diameter. Now, can you imagine? So something like this. Okay. So basically, this represents my inductor. Now you find there is a gap between the two coils or two turns. So it will give like to a capacitance. It will also give rise to a capacitance. It will also give rise to a capacitance. It will also give rise to a capacitance. And because these capacitances are distributed, so we name as CD. So CD becomes my distributed capacitance. L is the normal, this one. And it is also made up of the material of the wire. So there is something, R is also there because of the material of the wire. So in this case, all these things, obviously, L is the desired thing. In this case, like in the previous case, R and C were the desired things. Other elements were this thing. So in this case, these elements becomes my parasitic or stray elements. Okay. So these are the two very serious problems. One, I told you about the parasitics, and the second one, and parasitics are much more important at high frequencies, because we have seen it is given as omega L or omega C and so on. So my how my equivalent circuit on the same line will look. So my equivalent circuit of inductor, how it will look? It will look like something like this. So there is a L part there. There is some R part also there, series resistance or small r, whatever you call. And then there is a distributed capacitance. And in this case, these becomes my stray elements. Just to give you a rough idea, so it will my equivalent circuit of L at high frequencies. It will be like this. Okay. So there will be a distributed capacitance, which I am totaling out capacitance there, and this one. Now, if I plot the same thing, I'm not going into the details for that again, but if I plot frequency, sorry, I go to the next slide to have a better plot. So if I plot frequency versus impedance of the inductor, which is Z equal to XL, but it has certain other parts, XC and other thing. But typically it is XL is equal to J omega L is equal to J 2 pi FL and so on. And obviously it is again expressed in terms of frequency. So first we plot the ideal one. So this is the ideal. Like in the capacitor, it was decreasing, but this is the ideal inductor or perfect inductor because it is increasing with the impedance. But practically what will happen? Now, if I see a practical at initial frequencies up to the basic electronics, what you've learned, it remains the same. Then it will start deviating, but still behaving like an inductor. At some point, resonance will come and it will start decreasing. So again, if I divide into two categories, let's say this one. So my resonance will come here, okay, which means XL is equal to XC. But if you see here in this region, at least my inductor is behaving like a inductor because it is positive. It is impedance is increasing with the frequency. But here it is capacitive because your impedance is decreasing with the frequencies. And today, our frequencies of interest is this one. Now that is a challenge. Your resistor has almost become a short circuit of very small values. Your capacitor has become inductor and inductor has become a capacitor. Again, if I want to buy a good quality factor, just give me 5 more minutes. I think still we have time. So we defined by one parameter, which is what we call the quality factor, which is Q, just like we have for this one. And it is given as Q is equal to XL over Rs. That is inductive reactance over series resistance, or omega L over Rs, or 2 pi FL over Rs. So for a perfect inductor, it is very straightforward. R is parasitic here for an inductor. So Rs must be equal to 0. That means, and Q must be, obviously becomes infinite. The quality factor must be very nice. So that is something. And sometimes, because inductor we normally design on our own by taking the length of the wire, diameter of the wire, putting distance between the turns and so on. Typically inductors we design on our own. So I have various ways to increase the quality factor of inductor. How we can increase it? First is use a larger diameter, D of wire. Okay. What will happen here? If I use a larger diameter, your resistance decreases, and resistance is parasitic for, because R is equal to rho L A by A, and A is nothing. It is the area depending upon the diameter of the radius, which means your Q increases. R decreases, which is obviously not a desired element here, parasitic element. So that is one way of increasing the quality factor. Another way is possible by spreading the windings apart. I don't use the word diameter here, no, D here, because it will be confusing. Diameter or radius. Okay. Or increasing spreading the windings apart, the distance between them, let's say D. So it will happen, your CD decreases, because our aim is either to decrease the R, which is possible by increasing the diameter, because R is equal to rho L by A, or by spreading the windings apart, which will decrease the capacitance, because your C is nothing, it is epsilon A by D. A is equal to pi R square, and so on, which we know that, which means your Q increases. So either you have to decrease the R or decrease the C, which are parasitic, or sometimes because we want to increase the flux linkage, so increase the permeability, because here we talk about the permeability mu of magnetic flux linkage. Typically we use, say, air core between the windings. That means no material there. So we can use a ferrite rod. So we actually put the windings on a ferrite rod between the core. So which means your, again, Q increases. So basically what we do here, this is this one. So rather than having an inductor, this one, I insert some sort of a ferrite rod and put my windings across that. So this is how my inductor. So again, just to go for this, my inductor is used in LC filter also, in oscillator also, and sometimes to introduce the delay also, because delay is nothing, phase change, and phase is very important here. So this will discuss and continue with that. But basically, what we have learned in RF electronics, your RLCL will not behave like a simple RCL. They have parasitics associated with that. Like in the case of R, L and C will be the parasitics. In case of L, C and R are the parasitics. And in case of the capacitor, inductor, C and R are parasitics. So they are the parasitic elements are always there. So we always speak in terms of impedance. Never these values. Okay. Another thing which you have learned is measuring using a DC multimeter will not help, because we have to do the calculations all for the various parameters or specifications to get the best inductor or best capacitor and so on. So this is something. So applications are still there. Your capacitor is used as DC block, filter, oscillator. Similarly, inductor is used as a LC filter, oscillator, delay. If I have to introduce the delay, because phase is very critical here, I can't ignore the phase part. As I told you, not many fluctuations take place, not many amplitude and the phase change take place in the circuit, because lambda is nearly equal to the circuit size here. And inductor is also used as RF choke, just like uh, capacitor is used as a DC block. It blocks the DC. Inductor blocks the AC or the RF, and it will allow DC to pass through. Okay, but capacitor will not allow RF or AC to pass through. It will block the DC. So both the functions are different. So we used RF choke and so on. So this is something we have learned the basic. Now these are the parts of the transmission line, which we are going to discuss in the next one. So this is like a very important thing to understand. Then we'll understand, appreciate the value of transmission line theory, which I will discuss in the next lecture. And as per the new timetable, I hope 18th you will be here. You are supposed to be here, and we'll have offline lectures from there. So basically, we'll have 4 offline lectures, and till that time, till the 18th of this, we'll have online lectures. So that is something, a very good opportunity for us to interact physically also, even if it is for 4 lectures, but 2 weeks, it is a good time, which I am missing you in teaching. I am not also enjoying the teaching as I used to enjoy in classroom, but yes, when you come back, lecture theatre 2 is assigned for my course, lecture theatre 1 is assigned for the section A, and we'll have much more interactive and classroom session, which I am also looking very eagerly forward to, just like you are looking for. And so we'll continue with this, and transmission line, which you are going to start in my next lecture, will be a very interesting concept. I'll put in a very simple way, easy to understand way, so you'll enjoy. Again, my notes are more than sufficient. No need to refer to any of the book, but if you wish, you can always go after my lectures. So I stop it here. Any queries? Nothing in the chat box so far. Any query? But yes, now we'll have the time to discuss transmission line theory if any queries are there in the later part when you are physically on the campus. So nothing is there. So I stop